Hi, today we are going to discuss the Nios 2 pipeline implementation. So let's take a look at the table of contents and the topics we are going to cover today. So we are going to take a look at instruction architecture of the Nios 2 processor, and then we will discuss in detail about how the operation works stage by stage, that is the 5 stage pipeline implementation, and some general code and how the code works, and we will verify the output. So let's take a look at the instruction types first of all. So majorly there are three types of instructions for the Nios 2 processor. The first one is I type instruction, the second is R type, and then the J type. So the I type is the immediate type instruction set. uh, in the I type instruction set we can see the four blocks. A block acts as the source register and the B acts as a destination register. So immediate registers will be 16. So they will be like your instructions, and opcode is first where you store a certain code for the instruction to call it in the middle of a program. So R type is a bit similar to the I type. The main variations from I-type are the B acts as the target register and the C here is the destination. So you can see an extra block here that is written as OPX. Sometimes there will be a same opcode for two different instructions. So at that time OPX will be used to differentiate two instructions using the opcode as well as other different value. So coming to the J type, it will just have two blocks. That is, 26 registers will be acting as immediate register, and the 6 bit is opcode as usual, as we looked at I type and R type. So this is the entire block diagram of the Nios 2 architecture. So first of all, it is the program counter. So as we know that after every instruction, the program count will be increased by value 1. So here you can see every instruction will take 4 bits. So we will give PC plus 4 instruction to the adder. We can also here you can see the PC is joined with an adder. You can also change it, like in the code you can give like PC plus 4, so you can avoid the adder block. You can do that. So the multiplexers here, the, the multiplexer here, this works as first it takes the input from the adder, and as well as, yeah, so after that the from the instruction memory the data is fetched. You can see the four stages. It actually contains 5 intervals. This is fetch stage, this is decode stage, this is execution stage, and this is the memory stage, and this is the write back stage. So first of all, the data is fetched from the instruction memory into the onto the registers, and there the sign extend will act as if the first bit of the data is 1, that it will take all the bits of the input as 1, and it will send to the multiplexer. So the multiplexer will act as to differentiate the I type or whether the instruction is an I type or R type. Depending on that, it will select the blocks. And as we know that we have already discussed the OPX. So from then from the sign extend value, the registers will act as decoding the instructions in order to execute the required operation. So from there we move on to the ALU. So ALU performs the dot product that is required by us. So it will, so we have taken 6 inputs from one vector and six inputs from the other vector, and we are performing a dot product of them. So this process continues and will take six loops, because for every input it needs to send back the sum or the dot product of the vectors in order to add to the next loop. So let's take a look at code. This is a sample code that we got that the in the sample we have. So you can see the I type R type instructions have been differentiated clearly. So there you can see, take consider this example. So two R type instructions, multiplying and add, they both have same output, but they can be differentiating using the next value. So that's the work of that's the duty of OPX to differentiate. You can see the OPX is contained in the R type instruction set. So from there, this is the loop program. After every loop, if this condition, the branch less than condition satisfies, it goes back to the loop and again continues. If this is not satisfied, then it moves to the stop. So after, at the end, we can see the output in is stored into the R5 register. So let's take, after every loop, after every loop, the output will be stored in the R5 register. So that's it. That's here. So let's move on. So we have already discussed that every instruction will take 4 bits of data. So from here the loop starts, and at the 64, the final value, this here, you can see R5, right? It is the sum of A, that is source register, and the destination register. At that particular location, the value will of the final value will be stored. So this is the output we need. These values are given for the vector A, and these values are given for vector B. So this is the output after every cycle, and it needs to be added, and the final value should be 580. So let's take a look at the simulation and then come back here and discuss the output analysis. Okay, so this is how the console looks like. We have used models in here. It's mostly similar. So you can see the code for executing it is VCS plus V2K MIPS.V. These are all entire modules. We need to join them in order to we need to integrate them in order to perform the entire operation. So it is executing the design file, and now we can see the simulation. So dot slash simv will give the simulation for us. Yeah, so we got the window. So we can it's our we can drag all the items you want into the simulation window to see the required output. So we have come in the same order of the 5 stages of pipeline, like fetch and decode and execute. So first, till the PC out, it acts as fetching the data and reading, read data. All the commands will be considered as the decode, and ALU, ALU comes under the execution stage. So, and again, the write back commands are used to send back the data into the destination register. So this is the beginning of this cycle. You can see, just a minute. can see the simulation here. So after every cycle, the data is moving to the next stage to perform the same operation on the next inputs. So we know that we have seen that in total there are six inputs for each vector. So you can take a look at 3 is multiplied with 14 and we get 42, and this 10 is the previous value, so they both will be both these values will be added and it will give 52. That is the end of the second loop. So this we are considering this for example. So let's move on. So this is the final output of 432 and plus 148 will give 580. This is the final output. So we have used too many stalls in the program. That's why we have gone crossed 100 bits, because we have seen a sample at the beginning of the presentation. It just took 68 bits. So we have used too many stalls and we haven't cleared that. So now after completing the simulation, we need to give a flush command in order to make sure the program will the values are reset. So it keeps on moving. You can see that 104 and 128 again goes back to 116, and it will keep moving over there. So that's the end of the simulation. Now coming back, so we have seen that at the end of every stage the value is stored into the R5. So this is the test bench of our project simulation. So you can see the values of R5 after every stage it is stored into the R5. So 10 and 24 they are, so final output will be stored using the store word command, that is 580. So so as we have seen already in the simulation that this is the fetch store. It will the fetch this the main purpose of this command on this stage is to find the location, and the decode is bringing out the values from the registers, and execution process, that is multiplying or whether it is addition or yeah the given or division or the given commands, and it again write back to the memory. So you can see after 100 it again comes back up to the next loop, because it needs to continue till all the values have been executed. So here we have used stalling in order to avoid data hazards, and you can see the multiplication here and the addition here. They both combined, we call it the dot product. So we got the final output at the 116 bit, and again it has been sent back to 580. This is where the write back commands comes into the play. So you can see the branch has been reset to 0. So it keeps on moving here, and it will not go into the infinite loop. Thank you. So this is the end of presentation. Thanks very much.